What up guys, I have been playing a lot of Balatro recently and it is definitely a game I would recommend if you've not tried it. Basically the way that the game works is you're going to draw cards from a deck of standard playing cards and you're going to be asked to score over a certain amount of points. In order to do that you have 4 hands and 3 discards, so you can either play cards to score points or discard cards so that you can draw more from your deck and then hopefully score more points in the future. The amount of points you score for each hand is kind of based on the strength of the hands as they are from poker. So you can see that high card is the lowest strength hand and then straight flushes are the strongest hands. If you can score enough points for the round, then you get some money and you get taken to the shop where you can buy things to help you score more points in the future. So there are these things called jokers that can help you give you extra score for your hands, and there are these things called tarot cards that allow you to modify your deck, which is pretty cool actually. You can add cards to your deck, remove cards from your deck, make it much more consistent to draw the better hands. And yeah, I mean that's pretty much the basics. It's quite an easy game to get into. It is very complicated though once you get into playing it, because there's so many jokers, and they have different abilities, so there's so many combinations of things you can do to get the best scoring, and you do need to score more points every round in order to win the game. Score threshold's gradually going to increase as you get further through. But what I really want to talk about today is some of the probabilities of drawing your hands in Balatro. So this is a very common example of a situation you'd have where we got 4 diamonds out of a flush. In order to get the flush, we need to find one more. So if we were to discard these other cards, we'd be drawing 4 more cards from our deck. We can see here we've got 9 diamonds left out of the 44 cards. So how likely are we to actually find one of those diamonds, and how would we go about calculating this? So I think the most intuitive way to think about probabilities is by thinking about the chances of the events that you're looking for happening at each step. So if we were to think about drawing one card at a time, we could say that when drawing that card, we have a 9 in 44 chance of drawing the flush, since we have 9 cards that will make the flush out of 44 in the deck. And subsequently we then have a 35 in 44 chance of not drawing it. So after one draw we have the 9 in 44 chance of drawing the flush. Now let's look at the next draw. So we don't really care about any more along the top branch, because if we are to have already drawn it, we don't really care if we draw 2 of them or not. So those are always going to count as hitting the flush. But if we continue on from the bottom branch, in the next draw we're going to have a 9 in 43 chance of drawing one of the diamonds, because we've got 1 less card in the deck, but still 9 diamonds there. And then subsequently 34 out of 43 chance of not drawing it. So when we're now trying to think of the probability of having drawn it after 2 cards, it's going to be the probability of drawing it. It's going to be the 9 in 44 from drawing it on the first card, plus the chance of drawing it on the second card, which is 35 times 44 over 44 times 9 over 43, and that's actually going to equal 351 over 946. So not the nicest number. It's about 0.37. So yeah, not the nicest number, but it is what it is. That is how the probability works. So we could continue with this method. If we were to add another branch here for the third draw, it would be 33 over 42 down here and 9 over 42 up here. And we could continue working out the probabilities like that. I guess there's one thing to consider for this particular problem that we could use is the fact that really there's multiple ways of getting one or more of the diamonds, but there's actually only one way of not getting a diamond, which is to follow the bottom path the whole time. And in probabilities, the probability of something happening, so probability of A is equal to 1 minus the probability of not A happening, which is basically meaning that there's a 1 probability that something's going to happen. So either it's going to happen or it's not. And in this case, we'd actually find it easier to work out the probability of us not hitting the flush and then doing 1 minus that. So in this case, that would be 1 minus 35 over 44 times 34 over 43, which works out as the same. And that can definitely help us to work out the probability of more draws. And for 3 draws, that equals roughly 0.51, and for 4 draws it equals about 0.61. So obviously the probability is increasing each time. So we have 0.2 chance of drawing the flush after 1 card, 0.37 after 2, 0.51 after 3, and 0.61 after 4. So that method does work. And this is generally, you would call this the tree method of probabilities. And yeah, the tree method, like I said, I think it's an intuitive way of thinking about probabilities. I would say it probably works better in scenarios where the events are independent. So say when you're rolling a dice, every time you roll the dice, it has the same probabilities of coming out with each number. In this case, because we're drawing from a deck of cards, once we draw a card, it actually changes the probability of the next card because we can no longer draw that card. So we have like a different deck. So we've got to rethink about the probabilities. That's why we've, had to be updating the probabilities at each step as we go along to account for the fact that a card's been taken out of the deck. And while we have an answer for this particular case, it is quite difficult to generalize this to what if we had a different deck, different number of draws, we have to kind of rethink about it each time. And also, especially, what if we needed to actually draw more than one? So if we only had 3 cards for our flush and we needed to draw 2 of them, it would start getting more and more complicated. We'd have to add more and more branches on and be adding up more and more probabilities. So the other way of thinking about this problem involves sets. So first thing to say is that a deck of cards can be seen as a set of card objects. And what this means is that we have access to permutations and combinations. These are things that I assume you will have potentially heard of. I think it comes up in, maths class. I feel like I hear it every now and then. I will try and explain them fairly briefly. So the definition of a permutation is a specific arrangement of a set of objects where the order of arrangement matters. And when we're thinking about permutations, we are generally thinking about choosing k objects from a set of n objects. And how many permutations are there where we choose k objects from a set of n objects? And the notation is generally, so that's n, little n, big P, k. And a combination is a selection of items from a set with distinct members such that the order of selection does not matter. So basically saying, if you were to choose 1 and 2 as a combination, then 2, 1 wouldn't count as another combination. Whereas if you were talking about permutations, 1, 2 and 2, 1 would be separate permutations. Combination formula is written similarly, but with big C instead of big P. So again, we're choosing k objects from a set of n objects and saying how many combinations there are. Let's do an example, otherwise it probably isn't going to make sense. So the set of letters A, B, C, D, E. In this case, the set that we're choosing from has 5 members in it. So n equals 5. And let's think about permutations first. So again, we've got n equals 5. We've got, if we start with k equals 1. So how many permutations are there choosing one letter from this set? Well, it's actually pretty simple because we can just choose any of the letters and they each count as a permutation. So A is a permutation, just B, just C, just D, just E. That's all the possible permutations. Obviously there's 5 letters, so we've got 5 permutations. When k equals 2, so we're choosing 2 of the letters from the set, we can pick any letter first, A, B, C, D, or E, and then once we've picked a letter, there's only going to be 4 other options left. So if A is the first letter, there's going to be B, C, D, and E left. If B is the first letter, there's going to be A, C, D, and E left. So we end up having 5 choices for the first letter, and then 4 choices for the second letter. So we have 20 total permutations, choosing 2 objects from there. For 3 objects, again, we have 5 choices for the first object, 4 choices for the second object, and then 3 choices for the first object, since 2 of the letters have been used. If we've used A and B, for example, we've got C, D, or E left. So that's 60. We can continue on. Oh, sorry, that should be a 4. We end up with 5 times 4 times 3 times 2, which equals 120. And then if we're choosing 5 of them, then once we've chosen the first 4, there's only 1 left to choose, right? So we're not actually adding any additional permutations by adding in the last one, which is quite interesting. We'll write it like this though, which will make sense in a little bit. So again, there's 120 permutations, choosing 5 objects from there. Now, I think you can see the pattern here. There is a formula for this, but it involves a bit of notation called factorial. To not confuse this, let's say x factorial. So this is an exclamation mark. It's a little bit hard to draw. Sorry, but yeah, x exclamation mark means x factorial, and that is equal to x times x minus 1 times x minus 2, and so on until you get down to 1. So, a couple of examples of this. 4 factorial would be 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1, which is what we have up here actually, 120. So the formula for permutations, k objects from a set of n, is n factorial over n minus k factorial. And we'll just write one of them out. So set of 5, choosing 2, how many permutations are there? Well, it's 5 factorial over 3 factorial, which equals 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. We can just cross these out since they cancel out, and we end up with 5 times 4. So that's what we had here. Great, so let's do combinations now. Starting off with k equals 1. Remember, it's a similar concept, except we are counting different orderings as the same combination. If it's got the same actual letters, but it's just in a different order, it's just one combination, whereas permutations, they were being counted separately. So when we have k equals 1, it's still going to be exactly the same. There's no ordering to think about because there's only one object anyway. is A, B, C, D, or E. Again, we've got 5 combinations. Now, when we get to k equals 2, so thinking about when k equals 2, I think the best way to think about this is if we just pick a random combination, so let's say AB, how many permutations does that appear in? Well, it appears in the permutation AB, but it also appears in the permutation of BA, right? So A, B, and BA, they're both one combination, but 2 permutations. And if you think of any possible combination of 2 of these letters, it's always going to appear in 2 permutations. So the number of combinations for k equals 2 is just 20 divided by 2, which equals 10. Similarly, if we were to think about choosing 3 objects, again, let's choose a random combination, so A, B, and C. How many permutations is that going to show up in? Well, we've got A, B, and C, we've got A, C, B, we've got B, A, C, B, C, A, C, A, B, and C, B, A. Those are all the permutations that we counted over here, but they all now count as one combination because they're just different orderings of the same letters. So we have 6 permutations for each combination. And again, it doesn't really matter what the letters are. For any combination of letters, there's going to be 6 permutations. So we can divide 60 by 6, and we get 10 combinations. Now, to make this more general, if we're to take any combination, there's actually k factorial permutations for each combination. Because again, in terms of permutations, you could choose any of the available letters first, and then any of the other available letters second, any of the remaining letters third, and so on until you have no more letters left to choose. That's how many permutations there are per combination. So for k equals 4, we have 120. But in terms of combinations, we're dividing by 4 factorial, which is 24. So there's actually only 5 possible combinations. And similarly for k equals 5, it's actually 120 divided by 120, which equals 1. Which I think can see makes sense. Since it doesn't matter what order you pick them in, there is only one combination that involves all the letters because it's just all the letters. And if you're picking all but one, it's just whichever letter you don't pick counts as the combination. So that's why there's 5 combinations for picking 4 of them from a set of 5. I hope that makes sense. I don't want to dwell on it too long, but I do want to say that the formula for equals, so it's basically, as we were saying, it's actually just the number of permutations divided by k factorial. So we can substitute in that permutation formula, which was n factorial over n minus k factorial, but then we also need to divide by k factorial. And that is the formula for how many combinations of k objects can be made from a set of n objects. Great, so why am I talking about these? Well, it is quite relevant to a deck of cards. So if you think about drawing a certain amount of cards out of a deck, what you're essentially doing is you're picking a permutation of those cards, and if they've been shuffled, you're actually picking a random permutation. So assuming that the cards have been shuffled, which we are, then you actually have an equal chance of drawing any permutation. And since they're all equally likely, we can actually say that the chance of something happening, e.g. drawing the card for the flush, is equal to the amount of permutations that contain the card that we need, divided by the total number of permutations. So that gives us another way of working out the probability of A, or the flush in this case. Now we're going to modify this slightly and say, because, say if we're drawing K cards, then the amount of combinations is equal to the amount of permutations divided by K factorial. So the total number of combinations is equal to the total permutations divided by K factorial, but also the permutations which satisfy A. Since we're dividing the top and bottom by K factorial, it's not going to change the outcome. But it does mean that we can instead calculate the probability using combinations. And we prefer using combinations in this case because, well, firstly, we are really thinking about combinations because we don't care what order the cards come up in, just whether the card has come or not. But also because combinations, believe it or not, actually combine better with each other. So if I was to have some set of 5 objects and I was to choose 2 from them, and I had another set of 6 objects and I was to choose 3 from there, the combinations that involved 2 objects from the first set and 3 objects from the second set would just be the 2 object combinations of 5 objects times the 3 object combinations of 6 objects, which it wouldn't work the same in permutations. I'm not going to do an example of that, but you can try that if you would like. So let's apply this to our problem. So we have total cards of 44, and we're going to split this set into 2 separate sets. One of them containing the 9 cards that we're looking for. We'll call them outs. I think that's the terminology used in poker for saying that, yeah, we're looking to try and find one of those 9 cards. We then have a set of not outs, which I don't want the letters to get too confusing. Let's call the number of outs A. Number of cards which are not outs is T minus A, which equals 35 in this case. We are drawing 4 of these cards and we need to hit 1 of them. So using our formula up here, we need to find out how many combinations of cards contain at least 1 card from this A set, which contains the 9 cards that we want. And then we need to divide that by the total combinations. So total combinations, drawing 4 cards from a set of 44 cards, that is just the 4 object combinations of the set of 44 cards. And then let's figure out the combinations that give us a different number of hits of the cards that we're looking for. And we'll actually start with 0. So in order to get 0 hits, we would have to choose all 4 cards from that set of 35 cards that are not hits. So the number of combinations there is going to be 4 object combinations from a set of 35. For 1 hit, we're going to choose 1 card from the set of 9 cards that are our hits, so that we have 1 hit, and then we're going to multiply that by the 3 card combinations from the set of cards which aren't hits, because we're drawing 4 cards, so we need 1 of them to be a hit and 3 of them not to be a hit. We can keep going with this. So 2 cards, we choose 2 from the set of 9 and multiply that by choosing the other 2 from the set of 35, and so on for 3 hits. We choose 3 from the set of 9, so that should be a 1. And then for 4 hits, we simply just choose 4 cards from the set of 9 that are the hits. Amazing. So in order to figure out how many combinations actually satisfy giving us the flush, we're basically looking at all of these where we get 1 or more hits, since 2 or 3 or 4 still count as hitting what we want. So we need to add all these terms up and then divide by the total combinations. I'm not going to do this in my head, but yeah, let's get some values for this. And here are the numbers. So we have the most combinations of hitting once, fewer combinations of hitting 2 or 3 times. In total, we have 83,391 combinations of hitting 1 or more, and then 135,751 total combinations of choosing 4 cards. And that gives us a probability of 0.61, which, if you remember, is the same thing we got from doing this up here. Now, the observant amongst you might notice that that was way more complicated. And so why would we bother doing this? Well, this actually allows us to generalize the problem because we can actually create a formula for the probability for any initial conditions that we have defined by these 4 numbers up here. And also I would say it is easier for, depending on what those numbers are, this would actually be easier for figuring out individual problems. Like when you have a n, like if you need 2 or 3 and you're drawing like 10 or 15 cards, you don't really want to be doing the tree diagram for that. It's going to get very complicated. Whereas this, it's a simpler way because you're kind of listing all the combinations at once and then just summing the ones that you need. But yeah, as I said, we can actually write a formula. So I'm going to do that here. As I said, the problem is defined by these 4 terms here. So the big T is the total number of cards in the deck. A is the number of hits that we have or outs. D is the number of cards we're going to draw. And N is the number of cards that we need to hit in order to succeed. So if we needed 2 cards to get a flush, N would be 2. And here is the formula. So we're going to use this lovely piece of maths notation here, which basically means we're going to sum over multiple terms. And the terms are going to be the combinations of I objects chosen from the set of A objects times the combination of D minus I objects chosen from the set of T minus A objects. So basically we're choosing a number of hits from our set of hits and then a number of non-hits from our set of non-hits for different numbers of hits. And the amount of hits that we're interested in, we're going to start from I equals N, or number of hits that we need. So this means we start by substituting in N for I, or number of hits that we need, and then we're going to increment I and sum through all those terms until we reach certain limit terms, which are I needs to be less than or equal to draws. We can't possibly hit more than the amount of draws that we have, and similarly we can't possibly hit more than the amount of actual hits that we have in the deck. So I do appreciate this could be a little bit confusing, but we are basically doing the same thing that we did down here. So if we look at substituting in when I equals 1, that's when we're choosing 1 card from the set of hits and then D minus 1 or 3 cards from the set of non-hits. Then when we increase I by 1, we're going to figuring out how many combinations there are that give 2 hits. I equals 3, we're figuring out how many combinations there are that give 3 hits. And we're summing over the combinations that are relevant to us. So yeah, after all this talk about permutations and combinations, I hope that made a reasonable amount of sense, and we have ended up with a formula that we can use to figure out our probability of hitting what we need in any scenario, and we can substitute in these values depending on how many cards are in the deck, how many draws we have, how many of the cards that we want are in the deck, and how many of the cards that we want that we actually need to draw. And what I've done is written a Python function which uses this formula, so it can take the inputs of the 4 variables that we mentioned there and output the probabilities. which actually was really not too hard. The logic is really just that. In the for loop, Python got no problem doing a sum through a bunch of terms. And once I had this, I wanted to actually visualize like how the different values for those variables would affect it. So I just sent in a bunch of values for all the different variables and made some graphs out of them. And so this is what that looks like. We have parameters up here for setting the 4 variables that we talked about. They're currently set to the problem in question, where we're drawing 4 cards. Need to get one of them out of 44, and there's 9 cards that we're looking for in the deck. And then these graphs show how the probabilities change if each of these values change. So here we've got the 0.61 when we have 4 draws. If we were to have 5 draws instead, it would go up to 0.7, 6 draws 0.77, 7 draws 0.82. Over here is if we needed to hit 2 of them instead, we'd only have 0.18 chance. This is how it would be affected by having more remaining cards in the deck. Obviously, the more cards we have that are not hits, the lower chance we're going to have of drawing what we want. And if we had a smaller deck, then we'd have a much better chance of drawing it. Or less cards left in the deck. And then this is how adding more cards that count as hits to the deck would affect it. So if we had more diamonds in the deck, if we had one more diamond, it would go up to 0.66 instead. While we have this, I thought maybe we'd go through some other scenarios that could be interesting to see what the probabilities say. So I feel like this is one that happens semi-often to me, where we have a gut shot on a straight. So if we were to get a jack, we could have a straight there. We've got 4 jacks in the deck. We also have the possibility, there's 2 different flushes we could go for. There's the clubs flush or the hearts flush, where we have 3 of them. 9 clubs in the deck, 10 hearts in the deck, actually. So would it be better off for us to discard all the other cards and try and go for the straight, where we just need to hit 1 card? Or should we just be going for the flush? Even though we need to hit 2 cards, we have a lot more hits in the deck. Which one has a higher probability of us hitting it? I'm going to go with the club flush because I feel like it's rare to actually have 10 outs still. But so we're going to say 9 outs for the clubs or 4 outs for the straight. Which one would you guys go for? So let's fill these out. We'll do the straight on the left. So we have 39 cards in the deck, 4 hits that we need. And on the right we will do that we actually can draw 5 cards because we only have 3 of the clubs. We need to hit 2 though, 39 cards left, and there's 9 hits in the deck. I don't know why the colours are mirrored. I actually have no idea why that is. Bizarre. But yeah, so there is a higher chance of drawing the straight with 1 discard, even though we got to draw more cards here because of the fact that we needed to hit 2 instead of 1. It meant we have a lower chance of hitting both and getting the flush. If we had gone for the hearts flush instead, we would have had slightly better chance, but still less. Okay, is this right? Okay, it hadn't updated. It's 0.32, so still a little bit below. If we went for the hearts, we actually would have had a higher chance though, because of the 10 outs. It would have been enough. What is interesting though, is if we look at how the probability changes with the number of draws. So we've got, we're drawing 5 here. If we were to have 2 discards, we could draw 9 or 10 cards. And let's say we draw 9, and we draw 8 for the straight. Say we don't hit it in either case. Now it's, you know, fairly significantly better chance of hitting the flush with 2 sets of discards, and potentially you could even be discarding 10 if you didn't draw a single one on the first go. And then again, if we were to discard again, the probability is even more higher that we would hit the flush. So it's interesting how sometimes it's better if you only have 1 discard to go for one certain thing, and if you have 2 discards, then it's better to go for potentially something that you need to hit more, but you have more options in the deck. Also, interestingly enough, in this problem, if we were to decrease the cards remaining to 30, which I think is pretty reasonable amount to have, we would actually have a higher chance of drawing the flush off 1 discard than the straight. Obviously, if you have an open-ended straight, then you're going to have 8 hits anyway, so that's going to be a higher probability. But if it's a gut shot straight, sometimes it can be better for 1 discard, but mostly it seems like going for 2 cards on a flush is more consistent. Another thing I sometimes wonder is, should I keep an extra card in my hand to give me more potential outs? So, for example, in a scenario where I'm 1 card away from a flush, but I could keep 1 extra card and also have another 4 outs on a straight, or 3 or 4 outs on a straight. So this is if we had 9 outs and we were going to draw 4 cards, or if we had 12 outs and we draw 3 cards. It actually is slightly better to give yourself the more outs, even though you're drawing 1 less card, when you have 30 cards in your deck left at least. I suspect, okay, if we were to draw twice, we would have 0.97 chance, and here we would have also 0.97 chance. So if we had 2 discards, it would be similar between them both. But 1 discard, slightly better to have the more hits. A few other scenarios that might be interesting to you. So I think a fairly common one is, should you be trying to hit some of your gold cards? Say you already have your 5 card hand, and then you run out of discards, you want to use some of your remaining hands instead, as a way of trying to find a specific card in your deck. There are gold cards which can give you money if you have them in your hand at the end of the game. Problem is, every time if you use a hand, like just to play some stuff to get some new cards in, it basically costs you 1 gold. Gold card can give you 3 gold, so I guess it makes sense if you have a higher than 1 in 3 chance of drawing it generally. And I mean, you definitely don't if you only have 1 gold card in your deck and you're only able to draw 3 cards. 0.1 probability of you actually drawing it. If you have 2, goes up by nearly double. If you were to have less cards left in your deck though, if you have 2 gold cards in your deck, it becomes worth it at 17 total cards remaining. Though if you potentially can draw 4 instead, it would be almost worth it at 30 cards remaining, and it would become worth it at 22 cards remaining. Let's have a look at if you had 3 in your deck as well, just to see. So we're getting pretty close. So that would become worth it if you have 25 or less cards remaining in your deck. Actually not as worth it as I thought. I generally do tend to discard quite aggressively, or like play quite aggressively for the gold cards. But yeah, you need to have a fairly small deck or a couple of them to make it worth it seems. Though note that if you have multiple gold cards in your deck, you also have a chance of hitting 2 of them. At which point you'd be getting 6 gold instead of 1, so that would make it slightly better value. And 1, because I'm curious, let's say I had 8 aces in the deck, right? And I needed to draw 4 of them, like 4 of a kind aces was my hand. How many cards would I need to draw to make that likely? So if we draw 15 cards, we actually still have quite a low chance of finding the 4 of a kind, but it does go up quite rapidly, like as the amount of draws that we have goes up. So it becomes 0.5 with 23 draws. At 28, it's 0.73. And if we could get up to 35 draws, then we'd have a 0.94 chance. I mean, I'm sure reducing the size of the deck would have a huge impact on this as well. Yeah, so getting rid of 12 cards more than doubled the chance, and it's going to be 90% by the time you get to 26 draws. So there's always like, it generally, you know, the probability of hitting what you want will start off low and then it will go up quite rapidly and then obviously tail off towards the point at which you're guaranteed to hit it if you can draw that many cards. So there's always kind of a sweet spot in the middle where if you were able to have like 5 more draws or discards, you'd have a way better chance of finding your hand. So 16 compared to 21 here goes up to 0.71 from 0.4. So if you were able to, you know, get a discard voucher or an extra hand voucher, would massively increase your chance of finding a hand like this. Also, if we look at the hits in deck, we've currently got 8 of the card that we're looking for. If we could get that up to 12, again, we'd be looking at 3/4 chance. Obviously, if you've got more hits, you've got a more chance of hitting it. But there does become diminishing returns where going from 15 to 16 is not going to make a big difference in our chance to hit it. And we've also got a pretty reasonable chance of finding a 3 of a kind of a certain card. So this is a sort of a somewhat flexible system. If there's a set of cards that you know you want and you want a certain amount of them, you can use this to figure out your probability of getting it in a certain amount of draws. I will actually share this dashboard. I'll add a link to it so you guys can come and use this and have a play around if you want. I definitely found it interesting, particularly on the question of whether it's better to keep a straight or a flush, that it depends on the scenario of how many cards you've got left, how many draws you've got left. That's something that I wouldn't have known. I was just guessing at before. And obviously there's a lot more to Balatro than just the cards that you have in your hand. Like, a lot of it is about the strategy of jokers and what you should be buying in the shop, what you should be playing towards. But I've definitely found it useful to have it there for certain situations, in trying to make good hands in the early game and trying to figure out best ways to discard and use hands later on for value. So I hope you guys can find some use in it. I also hope you found this video interesting in general. Let me know how you found it and if you'd be interested in more content like this in the future. I have also been looking into some of the probabilities to do with like how likely you are to just draw a hand straight off the bat. So in your first 8 cards, how likely are you to have pairs, triples, flushes, straight flushes, all that kind of stuff. And believe it or not, it's actually way more complicated than, well, it's quite a lot more complicated than this problem we've been looking at today. But I can definitely share some stuff on that if there's interest. I will also be streaming Balatro at some point this week. I'll get that scheduled in. So if you're around, I will hopefully see you then. Have a nice day, guys.